Hey, this is my second example for rate laws. If you'd like to see more examples, go to mrrouse.com, and I have an explanation on all the stuff about kinetics. Look at the kinetics lesson and with more examples, and the handouts are located there too. But otherwise, just pause the video and give this one a shot. But I promise you, this one is a little trickier than the ones I've given you in the past. So let's get going. For this one here, I'm going to break this out in a little more detail than I did on the other ones because it'll become a little more clear of what, maybe even make the other ones a little more clear, and it certainly will make this one a little more clear. So for the first part, we're going to look at the first reactant. We need to find an example where the second reactant is not changing, such as in 1 and 2, but the first reactant is changing. So I'm going to choose these two, but let me write out the whole thing, which I don't normally do. And I'm going to put the larger number on top because I like it to end without being in fraction form. It doesn't really make a difference, but that's what I like to do. So I'm going to say experiment number 1 over experiment number 2. And when I do that, if I write out the rate law for it, the rate law would be the rate equals K times the concentration of the first reactant, so it's 0.25 to some power, I'm going to say x, times the second reagent, 0.1, but I don't know what order that x is, and I also don't know what order that one is, so I'm just going to put y, and again, that equals the rate, and the rate happens to be, in this situation, 9 times 10 to the negative 3. Now, I'm going to divide this by the second reaction. So that's also K times the first one, 0.1 to X to the X power. And the iodine is 0.1 to the Y power, and that equals this rate, 3.6 times 10 to the negative third. Now, if you notice, if it's the same on the top and the bottom, they can cancel out. So the K's cancel with the K's. This concentration cancels with this one here. And so now what we have is 1.25 divided by 1, which is, 2.5. 0.25 divided by 0.1 is 2.5. So the concentration went up 2.5 times to some power x. And I'm just simplifying this equation here. And that would be, remember these guys would cancel out with each other. It would just be 9 divided by 3.6 would be 2.5. So this would be 2.5. So what this is saying between experiments 1 and 2 is that A stayed the same, but the concentration of this polyatomic anion went up 2.5 times more concentrated, and it made the rate go up 2.5 times more concentrated. Therefore, X, what could this be raised to which power? 2.5 raised to what power is 2.5? It's the first power. So that's a first order reactant. So we just learned that this is a first order reactant. Now, that was important to go through these steps so that if you've understood that, you might help understand what I'm going to do for this next example here, because this next one looks a little deceptive. It looks a little confusing because why? You need to find an example where I is changing, the iodine is changing, but your first reactant isn't. But your first reactant's changing all 3 times. So that complicates things. I'm going to use experiments 2 and 3. I could also use 3 and 1. It wouldn't matter. I would eventually get the same answer. I'm going to use these two, and let me show you how this is going to set out and how things are going to cancel out. So 3 is larger, so I'm going to put 3 on top. So I'm going to put experiment 3 over experiment 2. And again, you could also do experiment 3 over experiment 1 because they're both changing. It doesn't seem to make a difference, but I'm going to do over 1. So experiment 3 is K times the concentration of the first reactant, to the X power. Oh, wait a second. It's not X though, is it, guys? We just figured out that it's first order. So let's put first power and not the X to the first power. So I'm going to put a 1 up here. We learned that that was first power. Times the concentration of of the second reagent, which is 0.3, to some other power. I'm going to put y equals the rate 2.16 times 10 to the negative 2 over the second example, that's k times 0.1 to the first power, 0.1 to the y power, and that equals 3.6 times 10 to the negative third. So these don't cancel out. We would like it to cancel out. That's a better way to set it up if you can, but in this case we can't. So we're actually just going to solve that. So k's do cancel out. So we're just going to say, all right, well, they don't cancel out, unfortunately, but we can say that 0.2 divided by 0.1 is just 2. So we can say 2 times, and the same thing's going to happen here, 0.3 divided by 0.1 is 3. 3 to the y power equals, let's do this over here, 2.16 to the negative 2 power divided by 3.6 to the negative, to the negative 3 power is 6. Okay, so I'm going to divide both sides by 2. I want to isolate and get this y alone, 2. So now I would say 3 to the y is equal to 6 divided by 2 is 3. So we learn that y equals first power. It's a first order also. So y is also first order. So see that trick there? Unfortunately, in the first one, we could see we got to cancel out these reactants because they were the same value. But in the second one, we couldn't, but we could actually just plug those values in because we knew the exponent and solve it there. So that's the trick. The last thing we're going to do is solve for k. K will equal the rate over, in this one, since they're both first order reactants, it would be over both reactants, and they're both first order, so we can just leave it at that. So let's just choose, I'll do the third one just because we can kind of fit it on the screen here, but you could choose any one of them. You'll get the same k as I do here. So k equals, the rate is 2.16 times 10 to the negative second, and the units are molarity per second. That's the rate of this reaction, molarity per second. So I'm going to put molarity over, I'm going to put second over here as a denominator. And also I have to put the concentration of my first one, which would be times 0.2 molarity squared times 0.3, oh, not squared, sorry, it's first order. So it's first order, we're going to leave it there. 0.3, also first order. So k equals 2.16 raised to the second power divided by 0.2, and that's also divided by 0.3, 0.36. Oh, and I forgot this is molarity. 1 molarity cancels with 1 molarity. You're left over with the seconds and another molarity. So your unit is molarity seconds. That's our value for k. And our rate law, I didn't write that, I should do that. Our rate law is rate equals k times S2O8 to negative times iodine. That's our rate law, and that's what k equals. And you need both of these pieces to answer the question. All right.